Hi, everyone. For those that do not know me, I am Srilata, and I've been with Solution Street for 6 years now, I think, and I am on the Delta project. And today I'm going to do a presentation on Docker for developers. What?
Hours work?
What's that?
Hours.
Yeah, they don't. I will put it
Oh, no. Slide?
I thought these were presentation notes. I'm on the browser. Okay, so the topics that we're going to discuss today are the virtualization technologies, and then what Docker is, and then Docker client-server architecture, and then a couple concepts, and then we'll take a look at some examples, demo, and then high-level concepts, and then close it down with some questions. So before there was virtualization, before there was Docker, we lived in a pre-virtualization world where we had a rack of servers. So with that, what we had was a physical server. On top of that, we had the operating system. And then the way we would deploy our applications is have all our libraries, dependencies installed, then the application deployed, and run the application. Now, what was the problem with that? The problems were many. For one, it's just one application, one server for one application. You cannot run multiple applications on one server. So then this application that you run on the server is utilizing only a fraction of CPU and memory. So everything else is a waste. Now, if you want to scale your application, then you'll have to purchase another server. And these commercial servers are not a joke. So you have to shell out a lot of money to get another server. Then it doesn't end there, because then you'll have to configure it all over again, and that's a laborious process. And then you will go on and run another instance or maybe a different application on that server, and you have one server running one application. So if you want to scale your application, then you'll have to keep buying more servers. So there's a huge cost involved there, and then the deployment process is slow, because then you'll have to go through the configuration, installation, deployment steps manually. And then once you're all settled down, and then you come to a point wherein you want to migrate it to a different server, say from an IBM server to a Dell server, then you'll have to go through this process again. And you might run into issues where, you know, the dependencies, the libraries, they don't quite gel with the operating system and things. So enter hypervisor-based virtualization, wherein you would have the physical server. On top of that, you would have the operating system, and then there is a hypervisor layer, which would allow you to install multiple virtual machines on top of it. And in each of these virtual machines, you could have your own application running. And in that virtual machine, it has its own operating system running. So it could be that in one virtual machine, you could have Debian running. In another one, you have Ubuntu running. In another one, Linux, etc. So it's completely isolated, and it doesn't matter what your host OS is. You could run virtual machines with any operating system within it. Now, with this, there are many benefits. One is cost efficient. So you don't have to buy multiple servers for how many ever applications you need to run. You could have one physical server, and then you could have multiple virtual machines installed on it, and then you could run either multiple applications or multiple instances of a single application. And it's easy to scale, because all you have to do is you create another virtual machine on that physical server if it has the resources. And then what's more, companies used to do this, used to get the physical servers, manually create their own virtual machines, and then install, deploy applications on that. But now, all this has been moved to the cloud. So with Amazon Web Services and Microsoft Azure, you don't even have to have the physical services on premises. So you can do this all on the cloud. So you can purchase a server, have how many ever virtual machines you want installed there, and have your applications deployed. And when you want your application to scale, all you have to do is click a button, create another virtual machine, deploy your application there. But there's limitations to this kind of a setup too, in a sense that all your virtual machines have its own operating system running. So the problem with that is there is resource duplication, in the sense that if there is Linux running there, so there's 3 Linux kernels running instead of sharing the host Linux features, Linux kernel features. So that would consume memory, CPU, and things like that. And when it's time to reboot, it would take longer, and they're heavyweight too. And if you have to port this setup to a different setup, then these hypervisors, from a different vendor, may not play well. So it's not all that easy. Now, after this, we've migrated to, or we've come a long way to container-based virtualization. With container-based virtualization, what you have is, instead of the hypervisor, you have a container engine. And this container engine is a daemon that would take on the heavyweight lifting of creating, managing your containers for you. And there's no virtual machines now. The container engine shares the operating system of the host. And you can have your applications running in containers on top of the container engine, which manages these containers for you. And within these containers, all you need to do is have your applications run with all their dependencies and libraries. So the benefits are manifold. One, it is cost efficient, and the deployment is fast because you don't even have to install virtual machines. All you have to do is just spin off another container on your container engine. And there's no compatibility issues. And compatibility issues and runtime isolation, they are tied together in the sense that if you have one application running in one container, and say if it needs JRE version 7, and then there's another application that needs a different version of JRE, then you can have that container install JRE version 7 and have application 1 running and have application 2 running in another container. So that way you have runtime isolation. And then, of course, there's better modulation and security because it's all encapsulated in one protected environment with no sharing and with tight security features. So Docker is one implementation of the virtualization technology. And this is the client-server technology wherein we would have the Docker daemon. It could reside inside the Docker host, and that's the one that's that's creating the containers, managing them, and also keeping a local copy of the images that you pull from the registry, and registry being a public, a place where you push or host all your images. And then Docker client is, the user wouldn't directly be interacting with the Docker host or the Docker daemon. There would be a client. There's 2 types of clients again. One is command line, and the other one is Keatmatic, which is a graphical user interface. So the user would enter commands on the Docker client, and the Docker client would then communicate with the Docker daemon and then get information about containers that are running, that are getting created, that are getting removed, destroyed, etc. So now the Docker daemon, it runs, or it needs, or uses Linux kernel features. So if you've installed a Docker engine or a Docker server on Linux, then you can have the client and Docker daemon, everything run on that Linux machine. But if you were to install a Docker, you cannot install a Docker daemon on Windows machine or OS 10 because they don't have Linux kernel. So then on that, you need to have a Linux virtual machine installed on that machine, inside which you will have to run the Docker daemon, and then that way you can get going. Okay, moving on to Docker concepts. We deal with images and containers. What is an image? An image is a read-only template from which you create containers. If you were to liken this to classes and objects in Java, an image is a class. A container is a runtime instance of a class, in this case, image. class, object, image, and a container. So without an image, you cannot create a container. And with an image, you could create multiple instances of the container. And then you can create images using Docker build. Or sometimes what you can do is you can create a container, make changes to that container, and then you can commit those changes. That way, you're writing on top of that image, the image that the container had built on. And then when you commit those changes, you're creating another image. And then an image always is composed of layers of images. So if an image has only one layer, that would be the base layer. And then on top of that, if you build another layer and then commit that, that would be another image. So image is nothing but a stack of other images. And then you store an image in a Docker registry. You could host your own registry or use Docker Hub. And then registry is where you store your images. Again, you can host your own registry or use Docker's public registry. And inside a registry, you have a repository. A repository is nothing but a collection of images, all with the same name, but different tags. Okay, so you can have an image and then maybe later you make some changes and then you version it and then you upload the same image, an image, a different flavor of that image, so it becomes tagged with another tag, but then it resides in that one repository. And then, yes. So we have, we could go to Docker Hub right here, and is that big enough for you guys? So you can explore here. You see all these images, Nginx, BusyBox, Redis. So you have, and then most of these are official. So general rule of thumb is if you are looking for an image, then use the official ones as opposed to ones that people have privately uploaded, because there's better documentation there. And then they also follow best practices, and they also it caters to the most common use cases. And one way to tell the difference between an official one and a non-official one is it's marked as so, official. And the ones that are not official will have a namespace. So MySQL's official image is that, and then this is something, MySQL Server is something that a private party, somebody else had uploaded. And then you can see how popular an image is by the number of stars and then by the number of posts that were made on that image. And then Docker Inc., which is the company that built Docker, has a dedicated team for reviewing and pushing content. So they take extra care with official repositories. So it's always better that you go with official images, and also security updates, they happen in a timely fashion. So you're safe. You cannot go wrong with official images. Let's take a look at a couple examples. I have Docker installed here, and then you can take a look at Docker's version using -- version. And if you want information on Docker, then it will give you information about the number of containers running, paused, stopped, etc., and the number of images. I have 3 images right now. I pull them just in case, because if I run an image, then if it's in my local repository, then it would just run it. But if it's not in my local, then it would go grab it from Docker Hub, and then that would take some time. So I already pulled a couple, so it doesn't take too long. And so the way you would spin up a container is you would just say Docker run an image. In our case, let's do Ubuntu. So what happens here is, you don't know what happens. So Docker PS is a command that you would run to see the containers that are running. Right now, there's no container that is running. So if you do Docker PS all, -A, it would tell you that Ubuntu, there was a container that was created with the image Ubuntu, and it was created 15 seconds ago, and it exited. So if I was running a container, why did it exit? Why did it die? That Ubuntu image is just a base Ubuntu image wherein you have the operating system. It's not running any service or application. So that's why it was, when you spin up a container, it spins it up and then there's nothing to run, so it dies. So one way to keep it alive is docker run. If I do this, then I have that container running now. So because I can't do anything on the console there, let me go create another console. And now you see that there is one that's dead and one that is running. Now, if you want to stop a container, you can do this. And then the container ID is a bunch of characters, so you don't have to type all the characters. So if I want to stop the one with ID 506, E9, etc., 506, I do that. And if I do docker PSA, that was already done. So let me stop the previous one, which is EA. So it takes a while, and then it will spit out the ID of the container that it killed. So now if you do docker PSA, now both of them have exited, and the one that I killed has an exit code 137, which means it was force killed and it did not exit by itself. Now, if I were to restart the same container, then I would go restart it that way. And if you, again, because that is just the base Ubuntu image, it ran and it exited. So let me restart the other one, EAC, and see that it's up and running. Now, when you stop a container, the containers are still lying there, using up space. So you are better off removing that container. And the way you remove a container is docker rm EAC. Okay, I cannot remove a running container. So this is removed. If I see there's one container that's still running and the other one got deleted. Now, if I do docker, say, run CentOS, I don't have this image on my local. So when I do this, what it does is it looks for it in my local. If it doesn't find it, it goes and grabs it from the Docker Hub. And then it downloaded it and it ran it too, except it's just like the Ubuntu where it spun up the container and then immediately exited. So if you want to grab an image but not run it right then, so what you can do is do docker pull. In my case, I'll grab another one. It will pull it, but then it will keep it in your local and not run it just that second. Okay, now if you want to take a look at the images that you have on your local, this is the list right here. And let me run Jenkins. Jenkins is a build and continuous integration tool. So they have a web app for that. So I grab the image and I'm running that image now so I can access Jenkins on the UI. It's up and running. So Jenkins is run on port 8080. But I'm not able to reach it. The reason is the container, it's running in a container, and it's not exposed to the external world. And I am trying to access it from my host. So what I need to do is expose my local hosts. I have to map the ports. So the port on my host is routes traffic to that port on the container. So the way I do it is, say docker ps-a is that. Now if I'll go and kill Jenkins and restart it. Docker. Oh, it's still run. Okay, I exited that. And then what I'll do is, using the -p option, I'm doing a port mapping wherein 8080 on my local host is mapped to 8080 on the container. And then say, run my Jenkins. When I do this, Jenkins is up and running. I can access it, but then when it's up for the first time and you don't have any logins created, what it does is it creates a user for you, and then there is this password that it gives you. So you take that password, you put it in there, and you can log in. After that, you can go and install whatever plugins that you want, and go about creating more logins, jobs, and set up whatever you need to set up. That takes a while. You can see here in the log that it's doing, it's downloading libraries, plugins, etc. Once that's done, I could go and create a user. So let's say admin2, and I'll give it a password. And then say, now I could go and create new jobs here, and let's say I could log out and then log in with admin2, the user that I created just now. I can log in. Let me create a job, and then just say test job. And then it's a freestyle project, and then hit OK. So I have my Jenkins up and running. I have set up user in this case, but then you could also select create multiple users, create jobs, set up your jobs, and then have it. But now next time when this crashes, or if you have to stop the container, what happens to all that data and the jobs that you've created? Let's take a look. Docker. So we have 203. So it's shut down. And let's go. The site is no more available. Now let's run it again. On the same port. Now this time when we run it, it's going to be a new container. And this container is brand new. It doesn't remember anything from the previous container. So the users and jobs that you've created there are lost. So you're presented with the screen because it's not giving you the login screen because there's no users, and you have to log in with the default user that it has created with the password that it gave you. So one way to circumvent this is just like how you've done the port mapping, you can map the volumes too. So we have a host, and then we can create a folder in our host on our host, and then map it to the directory where Jenkins saves all its data. So var Jenkins home is where Jenkins saves all its data. So when we map those two, and what happens is when the container is running, it makes a copy of all that data externally on the host. Next time when you spin up another container, that information where it's saved on the host is what the container uses, and so you have all your information intact. Let's do that. The way you do volume mapping is let me kill those two containers that Docker had spun up for Jenkins. So you have Docker stop create a So I just want to remove all the containers that have been created. So I do this, then it removes all containers. Now let's go ahead and run Docker Jenkins by doing a port mapping using -p option, and -v option is what we use to map volumes. Let me go create a directory here that would take in Jenkins data. So I would create Jenkins data. So I have, so it's an empty directory. And then I would say my home directory, Jenkins data, is mapped to var Jenkins home. Jenkins underscore home. And then I run Jenkins. Now, because this is a brand new container, first time over, you'll have to establish all your data, create it, and the next time when you log out and log back in, then you will have it available. And this is the default user's password that it has created for us. Let's go in there. And then. So we have this. And you could do this all over again, or let's just skip that part. And let me go create manage Jenkins, or maybe people. Let me go create users. I'll go create another user. Admin 2 again. And then I have another user here. Let's go back and create a job. Because I haven't installed all those plugins, I don't have the other options to create projects. So I save this. Now if I see, I have test job too. So let me not just log out. If I log out and log back in, anyway, I'll be permitted into the application, but let me go kill it and come back in to see whatever I created is still intact. Docker. There's nothing running, so let me go back and run Jenkins one more time. It did not give us that default screen where you have to enter that big password because it already remembers your information and it knows that you have users created on that system. So it gave you the login screen. You enter the user credentials that you've created previously and you will see that you are let into the system. And if you were to look at test job 2 that you had created before is here. So every time you run a container, you cannot be doing port mapping on command line. That would be tedious if you have multiple applications running in multiple containers and then you have to have them communicate with each other. So how do you do that? There comes Docker Compose, which is where you just like, it's just a YAML file where you mention, okay, this is how my configuration is. This is how I'm mapping my ports. This is how I'm mapping my volumes. You have that in a file. And then anytime you want to create all your containers and have your system running, all you do is do Docker Compose up. And then it'll take care of building an image and running a container off of that image. So we'll take a look at that. So let me kill this. So I had saved that in so I have my Docker file here, and I have my Docker Compose YAML file. So in here, what I'm doing is, what I'm saying is I'm using version 2 of YAML. And then I'm saying Jenkins built from within that context. And the port mapping is done and the volume mapping is done here. So I have a different folder, my Jenkins data here. But then I was playing with it yesterday, and then I created a user and then also a test job. Let's see if I do Docker Compose up here. Let's see if I can get my Jenkins running. So it runs off of that Docker Compose YAML file, builds an image, and then runs a container. So when I did that, it took that information from the Jenkins data that I had, and I no longer have to enter all those tedious commands on the command line. So the test job 2 that I'd created before is lost because this is just a spin up a container from a new data store. And I wanted to discuss, so there's two ways of creating an image. One is you would write a Docker file. A Docker file is just a simple text file with no extensions, and it would start with a capital D and everything is small case. Then you would put in a set of instructions with arguments, and then you issue the command docker build, and it builds an image for you. The other way is you run a container, and then within that container, if you make any changes to that container's file system, so the difference between a container and an image is that image is read-only, and it has different layers. Container is also full of layers, but then it also has an additional writable layer. So whatever happens in the container, it keeps writing to that writable layer. Once you say commit, everything that's in the writable layer is committed, and an image is created out of that. So you can save that image, push it up to Docker Hub, and then use it from there. You could start from scratch wherein you write a Docker file, create an image, push it up, or you take an existing image, make modifications on the container, commit those changes, push it up. Let's try and take a look at that. Okay, so I have a Docker file right here. I have nothing but one line. It says from Jenkins. The first line of your Docker file should be with the instruction from. It has to always start with a base image. Without a base image, you cannot build an image. But that would be your parent image. But how? So you have an image. It has a parent. That image has a parent. That image has a parent. But then where do you start? What would that base parent image have if it doesn't have a from? So when you're starting an image from nothing, what you say is from scratch, and then have a set of instructions in there, and then that's how you come up with your very first image. And then you can build on top of that. So for my example here, all I'm doing is I'm building my image from the base Jenkins image. Now, the way I can build it is say docker build -t, I can give it a tag, and then call it, because it's not an official image, my repository will have the namespace Srilata Kandi, and then I'll say my Jenkins. And then when I do the dot, so I'm giving Docker the context. The context is D, wherein all the files from here are taken into consideration when it's building the image. Say if I have any files on my system there, and then it needs those files to be copied onto the image and run at the time when I'm spinning up the container, it grabs those folders and it has them available. Also, it looks for Docker file in that context. So it successfully built that image. So the way I push it up to Docker Hub is saying docker push my tag. When I don't specify a tag, it automatically tacks on latest to it. It's advisable that you always put a tag, because when you run a container off of an image without mentioning a tag, it grabs the latest. Latest doesn't always mean the latest and greatest. It's just that the tag happens to be latest on that. So if I go here, and this is my dashboard, I do not have any repositories before, but right now when I pushed it, it goes and pushes it up to Docker registry, and just a few seconds ago, I've pushed the latest tag. So if you were not logged in before you do a push, it would ask for your username, password, and all that stuff because they are already logged in. It was using my credentials from before. That's one way to create an image. Let's do another, the other way, wherein you would just say Docker run Ubuntu, say, and then, now if I do this, it would just create the container and then exit. So there's no point. So the way I would do it is I would do -IT, wherein I'm doing it in an interactive mode with the standard input and output available to it. When I'm doing that, I'm inside that container. So let me run git there, and git isn't available. So let me do apt-get update. And now when I'm doing this inside the container, the file system inside the container is getting modified. Get install. Now if I see git, git's available. Now, if I take a look at that container, I can now take the container and say Docker commit that container, because whatever changes that happen on the file system would now be committed. So, and then this is the image that it created. I could say, okay. So it doesn't have a repository, so let me do now it committed those, and the image that it created should be /ubuntu git. So I see that right there. So let me push that, Docker push. And if I say use the tag 1.01, oh, that's not the tag that it got created with, so it's not available. So you see that I published or made that image available on my Docker Hub. So if I were to run this now, instead of Ubuntu, I will have Ubuntu with Git available on my container. And then I wanted to take you through another example where, so if I let me run Tomcat, because I have the Tomcat image downloaded. It goes by faster because I have that image locally available. Now, it can be reached because it's the same issue wherein we need to do the port mapping. Let me kill that. I have Tomcat available here. So if I have an application that has to run within a container using Tomcat, so what I can do is I can write a Docker file saying from Tomcat, and then if I have my WAR file, then I can have that be copied into the web apps folder of the Tomcat that is in the container when it's spun up, and then have it run that way. So I have a WAR file right here with a simple HTML file that says, hello, Srilata, and let's see if I can, so right now if I do that, it's not available because it's just the base Tomcat that I'm running. What I'll do is I have a so I have my Docker file here. So if you look at the contents, all I have is from Tomcat because I'm running Tomcat from its base version. And then what I'm doing is I have tree.war available here. All I'm saying is add that into the local Tomcat web apps directory. So let me Docker build -t. So I'll build this image. So it has two steps. Whenever it builds in layers. So the first instruction created a layer, and then the second instruction created another layer on top of it. And that's my image. Let me Docker run. So when I run this image that I just built, I will be able to go to localhost 8080/3 and then see that my application come up. It's just an HTML file. Okay, sorry. I'm trying to run Tomcat from Docker. Oh, because the container is not up, yeah. Let me, so it's up. Let me go kill that container. Let me go start it up. Because I have that image locally available, it doesn't take long. So that's how I run my application from within just that container. But taking a look at basic concepts of Docker, and then some commands and examples. What else is remaining? So these are a couple high-level concepts, Swarm and Compose. Compose, we've taken a look at, and Swarm is, it enables you to run multiple containers across multiple machines in a clustered network. So what you could say is, okay, I'm creating all these containers, and then I can have them available on a network, and then have that network communicate with another network of containers on a different machine. So you can create these multiple containers, assign one as the manager, and then all the others as reporters to that, and then the manager would take care of routing, traffic, and communication between all those containers. And network drivers. So there's 4 kinds of networks available on a Docker engine. The 4 types are bridge, host, closed, none, and overlay. So the default one is bridge. Whenever you spin up a container, all these containers are available on a bridge network. So they can communicate with each other via this network and also the host. So that's the reason when I had to port my 8080 port on the host to 8080 on the container, they were on the bridge network, they were able to communicate, and that's how the port mapping happened. And then host is where, the host network is where there is no isolation, in the sense that Docker host and Docker container, they have just the one network. So if you were to access port 8080 of the host, you are actually accessing port 8080 on the container. So there is no isolation. So it's security-wise, it's pretty, what do you say? It's not safe, and that you open your containers up to external elements, and therefore you'll have to be careful. You shouldn't be doing this in a production environment. Closed or none is where all networking is disabled. So when you create a container, it's just by itself and it's on its own island with no connection whatsoever with the rest of the world. So there's very few use cases that way wherein, I mean, you can have a container running by itself as long as it doesn't have to communicate with the rest of the world to get information from either the internet or something. So in that case, you can have a closed network, have your container running on a closed network, and maybe have a custom driver to just communicate with that one container. And then overlay container comes into play when you have multiple Docker containers strewn across multiple physical servers, and then you have to have communication going on between all of them. Bridge network is what is provided on Docker by default. What can be containerized? You can containerize almost anything. Operating systems, tools, databases, browsers, and even utilities like curl. And then these are a few companies that use Docker in production. And there's a few alternatives to Docker: Rocket, LXD, OpenVZ, Linux vServer, Windows containers. But Docker is at the top. There's moderate to low usage on all these other technologies, but Docker is right up there. Questions?
If I understood correctly, a Docker file is when you want to create your own image.
Yes.
And add different images in and create some sort of package.
Right.
Do you know what's the most popular use of Docker? What do most companies use it for when it's in use, or is it too varied to have one specific?
So within a company, say if you have your own setup that you're running your application on Windows and then somebody else is running it on Mac, then you'll have to go through the pain of installing, having your dependencies right and all that. So if you containerize it and then have the image saved, and then you're not even bundling it up, the whole thing, all the source code in it. It's just the image, and then you put it on Docker Hub, and then the other person can just grab the image and run it on his Mac setup. So it's shipping it off is easy, deployment is easy. So I don't know the real use cases where big companies, how they use it and all, but then this is one of the examples wherein, with very minimum pain, you can get started.
If you have sensitive information in the image,
Say that again.
If you have sensitive information in the image, you don't want to put it in the Docker Hub, right? Because it's public, and pull it down and look through the files and stuff.
Maybe. So you have your Docker Compose. So you put all that information into Docker Compose and then have that build the image. And again, your image is read-only. So there's no way that you put up your image there, and then somebody grabs that image and then opens it as a Docker file, right? So the image can only spin up a container. You cannot go back and then get to the Docker file from an image.
But if you have like sensitive information in the image itself, like if you have something set up with like, I don't know, a security key or whatever that's there read from a file, then they can just.
I don't know the answer to that. I don't know if they can reverse engineer from an image and then get to that sensitive information. But then there's always Docker Compose, wherein you have all that information there. You spin up. Again, it would be the same thing as if you had created your image from a Docker file. Again, you're not exposing your Docker file. It's just the image that you're exposing. I don't know the answer to that.
Well, I guess what I'm asking is, like, from an image, you can just log into and you know what I mean? Like, you can just log into the command line and start running.
Right. You can run a container. Again, you should be smart enough to not put that information where people can easily access it. But then if you are containerizing your application and you want people to use it, then obviously you'll do that and then put it up there, right? Anything sensitive, you won't. Then again, you want certain aspects of your application to be available and then safeguard your sensitive information. I don't know how you would do that.
You can have images not published out there for everyone else, right? So it's perfectly okay within a company to have unsensitive images that are reused.
You can have your private namespace, private repository, and then you can, you don't have to make everything public. Any more questions?
Kai, can you give us a 30-second overview of how we're using it on Aderix? Because that is an answer to just a question. Just quickly, how we're using Docker, or maybe if Kenny wants this.
So, we build those images that we kind of have them in the repository, and we build images with specific